In this video, we're going to look at this rack and pinion system, and we're going to look at how to derive an expression for the acceleration x double dot two different ways. First, by using our equivalent inertia method, and then second, by using free body diagrams and our force balance equations. Now, what is a rack and pinion system? So a rack and pinion system is what's drawn right here. We have this gear, and this gear is attached to this object that moves linearly. So pretty much we can attach a motor onto a gear and that's going to spin. But we can have an output of linear translation from the rack over here, which is pretty cool. So we can input some type of rotation and we can get some type of translation. Now, for this problem, we are going to write our acceleration in terms of T, which is the torque applied, in terms of R, which is the radius of this gear, in terms of IS and IP, which is the inertia of the shaft. The shaft is right here. We would attach that to a gear or something. And P, which is the inertia of the pinion. And we're going to write it in terms of MR, which is the mass of the rack. So now we're going to work the equivalent inertia method first. So this is part A. Now to figure out the equivalent inertia, we have to look at our kinetic energy. So the kinetic energy of each of these parts is going to be 1/2 I omega squared plus 1/2 mv squared. And these terms have different, they mean something different. So this right here is my rotation. This right here is my translation. So when I look at this, I'm going to start with this gear. So this gear only is going to be rotating. So I'm going to have 1/2 I p omega squared. So we're going to be rotating with some angular velocity. And that's just, we're going to call it omega. Now, this shaft is rigidly attached to this pinion, so they rotate at the same speed. So this is going to be plus 1/2 is omega squared. Right? If these are rigidly attached, as I rotate this with the some angular velocity, this is also going to rotate with the same angular velocity. And again, the shaft is only rotating. So now I look at this rack or this linear piece, and this linear piece is only translating. So the linear piece doesn't have any of this rotation. All I have to account for is this 1/2 m, so mr, v, we're moving like in this direction, so we have some velocity, squared. But if you remember from one of my previous videos, we want to pretty much write this in terms of omega. So we want to, or our angular velocity. So we need a relationship between omega and our velocity. And how we do that is we can look at this relationship. So this distance is equal to r times the distance, the angular displacement. We can differentiate, so our velocity is equal to r times omega, and this is what we're going to use right now. We can differentiate again, and we get our linear, our acceleration is equal to r alpha. So we want to put this v equals r omega into the equation right here. So we get this is equal to 1/2 IP omega squared plus 1/2 IS omega squared plus 1/2 MR. We have to square both of these terms, so we get R squared omega squared. Okay, so now each of these terms has a 1/2 and each of these terms has an omega squared term. So we can write our energy. It's going to be equal to 1/2 times IP plus IS plus MR, R squared, times omega squared. And this term right here becomes our equivalent inertia. So now what we can do is we can use the equation. The sum of our moments is going to be equal to our inertia and our equivalent inertia times our angular acceleration. And I'm going to write angular acceleration as theta double dot, and I'm going to write acceleration as x double dot. So that's what we're looking to do right here. So let me change this. This is equal to theta double dot. So now what is the sum of our moments? Well, right now we only have a torque, and I said my convention is x is to the left is positive, y up is positive. So that means anything that's going clockwise in this case is going to confer with the right hand rule and is going to be positive. So we're going to have t is equal to I-E, my moment of my equivalent inertia, times theta double dot. Now, theta double dot, well, let's put in theta double dot first, because theta double dot, I don't want to express this in terms of theta double dot. I have an equivalent expression right here where theta double dot is equal to x double dot over r. So my angular acceleration is equal to my acceleration over r. So this is equal to IE, torque, is equal to IE times x double dot over r. And I can multiply that r across. So I get, let's go over here. So I get, and let's do it in terms of capital R, right? Because capital R is the notation I was using. So all these really should be capital. But if I multiply that through, I get RT is equal to IE times x double dot. I just need to substitute this IE, divide it over, so I get x double dot is going to be equal to RT over IP, the inertia of the pinion, plus IS, the inertia of the shaft, plus MR, the mass of the rack, times R squared. And this R should also be a capital R. So this is the expression that we have for acceleration using equivalent inertia methods. So now let's do this again, but using free body diagrams. To do the free body diagram, I have to draw a free body diagram of the gear, and I have to draw the free body diagram of the rack. And I'm going to simplify it. I'm just going to use it. I'm just going to do a circle, and I'm just going to do a rectangle. So I'm going to put the forces that I know on here. So this is some torque T. Now I'm just going to say that my inertia is going to be equal to IP plus IS. So I don't need to draw this shaft in, but they're attached rigidly. They rotate together, so their inertia is added together. And we have a radius R. Okay. We have a mass R over here. We're going to use the same positive directions, but we do need to take into account the reaction force between the rack and pinion. So as I rotate this way, when I get to the bottom over here, I'm exerting a force on the pinion, on the rack, that's to the left. The rack exerts an equal and opposite force back on the pinion that is going to be to the right. So we're just going to call this some force F, and this is that force F here. When we're drawing the free body diagrams, we want to draw the reaction forces, not the forces that they apply. So this is the reaction force on the gear. This is the force that's exerted on the mass. So these are our free body diagrams. I'm just making sure I didn't miss anything. Torque, force, no. So now we can go to our equations of equilibrium. For this, right here, this is rotation, so we're going to have the sum of our moments is going to be equal to our inertia times our angular acceleration, and I'm just going to write it as I double dot. In here, we're going to have the sum of our forces is going to be equal to mass times acceleration, or x double dot. And this is going to be the positive way. To the left is going to be positive. So let's sum our moments. Well, we have the force, the moment of T, this torque right here. Then we have a moment with this force. If we rotate it clockwise, we're going to go tail first. So we're going to be minus F times R going from this point. So F times R is equal to I is equal to IP plus IS times our angular acceleration. We have the same relationship between angular acceleration and our acceleration. So we can say this is T minus FR is equal to IP plus IS times our acceleration over R. Multiply R across, so we get TR minus FR squared is going to be equal to IP plus IS X double dot. Okay, so now we're almost there, but we have this F term. Luckily, let's go and look at this equation because that also has the F term. So F to the left is positive, so F is equal to mR times X double dot. So now we have an equation for F that we can plug in right here. When we plug that in, we get TR minus mR X double dot R squared is equal to IP plus IS X double dot. So let's move this to the other side of the equation. T times R is equal to IP plus IS X double dot plus MR X double dot R squared. And now both of these terms have an X double dot in it. So I can say this is equal to TR is equal to IP plus IS plus MR R squared X double dot. And now divide this, which was our equivalent inertia, but divide this. So I have X double dot is equal to TR over IP plus IS plus MR R squared. So now we've derived the acceleration using free body diagrams. And my terms are backwards RT and TR, but these right here are equivalent to each other, right? All my terms are the same, RT over IP plus IS plus MR R squared. And if you had more inertia terms or whatever, you would keep adding them to get your equivalent inertia, and you would go from there. So hopefully this video has helped. It showed you two different methods to derive acceleration from us that you could expect to see in a system's dynamic problem.